students, welcome to EPG Pathshala. In today's module, we are going to discuss on components and types of wind turbines. Wind energy is based on the kinetic energy, which is converted into the mechanical energy or the electrical energy for various uses. We are using the wind energy from ancient times either with the help of windmill for grinding the grains or for pumping the water. But recently, we are using the wind energy more for the electricity generation. And this is based on wind energy conversion system. So, in today's module, we are going to discuss on what are the components of wind energy conversion system, especially the components of wind turbine, which is the major component of wind energy conversion system. We will see the different parts of it in detail. We will see functions of each component, each subcomponent, and also the classification of wind turbines, especially on the axis orientation, that is horizontal axis wind turbines and vertical axis wind turbines. What are its advantages, disadvantages. We will also see the designing of the wind turbine, what all things has to be taken care while designing a wind turbine. Let's start with the basic components of wind energy conversion system. The main components of a wind energy conversion system which is used for the electricity production are aeroturbine, gearing, coupling, electrical generator and the controller. So, this figure shows the basic components of a wind electric system. Here, the wind turbine converts the energy in the wind to rotary mechanical energy. It is capable with the help of pitch control and yaw control for proper operation. The step-up gear and a coupling constitutes mechanical interface. This helps in transmission of rotary mechanical energy to an electric generator and power output is connected to the load or the power grid. The yaw control is fixed in wind turbines in the areas where there is change in wind direction. A motor rotates the turbine slowly about the vertical axis so as to face the blades into the wind. The controller helps in sensing different parameters like wind speed, wind direction, shaft speed and torques at various points, power generated and temperature in the generator. It also senses the control signals for comparing electrical output to the wind energy input. This also protects the wind turbine system from extreme conditions like strong winds, electrical faults, etc. So, the basic components of a wind electric system consist of aeroturbine, gearing, coupling, electrical generator and the controller. Let's see what a wind turbine is. It's a system that converts the kinetic energy available in the wind into mechanical or electrical energy. So, it is the most important part of a wind energy conversion system. Different parts of a wind turbine system, you can see in this picture the different parts of wind turbine. It includes foundation, tower, nacelle, hub, rotor, drivetrain, gearbox, generator, electronics and controls, yaw, pitch, braking and cooling. The parts of this wind turbine system are grouped into rotor, windmill head, transmission and control and supporting structures. The rotor, there are two types of rotor, which is horizontal axis and the vertical axis rotor. The vertical axis machines operate in all the wind direction and there is no need of yaw adjustment. The windmill head or turbine, it consists of rotor, housing of the rotor bearings. It houses control mechanisms incorporated like changing the pitch of the blades for the safety devices and tail vane to orient the rotor to face the wind. Transmission and control. This part, the rate of the rotation of large wind turbine generator operating at rated capacity or below is controlled by varying pitch of rotor blades. The transmission options include mechanical systems involving fixed ratio gears, belts and chains singly or in combinations or hydraulic systems involving fluid pumps and motors. Fixed ratio gears are recommended for top mounted equipment and also it consists of the supporting structures. The wind turbine converts the energy in the wind to the rotary. Now we will see the components of wind turbine in detail. Rotor, the component of wind turbine that is rotating and helps in the conversion of kinetic energy to mechanical energy. It consists of blades and the hubs. What is a hub? The function of this hub, the rotor hub, is to connect rotor blades to the rotor shaft. This component controls the power generation of the wind turbine. Blades. This is a rotating component of the system. This component is based on the principle of lift and drag or the principle of aerodynamics. It converts kinetic energy first to mechanical energy and then transferred through shaft to generator for converting into the electrical energy. Commonly, 2 or 3 blades are used in the wind turbines or having in the wind turbines. The wind blown over the blades lift the blades and rotate it. The 2-bladed wind turbines have lighter hub and so the whole structure is lighter. But 3-bladed wind turbines are aerodynamically efficient and it is having low noise. The length, so commonly we are using or we are having the 3 blades in the turbine. The length of the blade is also an important parameter for the estimation of wind power generation potential of a wind turbine. The torque increases with more number of the blades. So, the number and the length are important factors. The blades are commonly made from composites, mainly fiberglass or glass reinforced plastics or carbon fiber reinforced plastics. Wooden or epoxy laminates are also used for making the blades. One parameter associated with wind turbine is the solidity. It is defined as the ratio of the projected area of the rotor blades on the rotor plane to the swept area of the rotor. So, the solidity is depending upon the blades. So, high solidity rotors use force for rotation and these rotor turn slower, while low solidity rotors have slender aerofoil and these rotors use lift force for the rotation and turn faster. Chord. It is the width of the blade which is across the distance from one edge of the blade to the other edge, that is the chord. Drivetrain, this consists of flow feed shaft, gearbox and a high speed shaft. It also has support bearings, couplings, brake and rotating parts of a generator. Nacelle, this is the covered part of a wind turbine system over the top of a tower. It houses gearbox, low speed shaft and high speed shaft, generator, controller and the brake. It has an important role in the protection of components of wind turbine from various weather conditions. It also helps in the reduction of noise that is produced from the rotation of wind turbine. So, the nacelle is the covered part. Low speed shaft. This shaft transfers torque from rotor to the drivetrain. It is a rotating part present on the rotor side of the turbine. The connection of this low speed shaft increases rotations per minute. The rotor weight is also supported by this shaft. Gearbox. The function of gearbox is to step up the speed as per needed by the generator. The low speed shaft is connected to the high speed shaft with the gears. It increases the rotational speed that is required for the generator to generate electricity. The increase in rotational speed is of the order of 30 to 60 rpm, from 30 to 60 rpm to 1000 to 1800 rpm. This gearbox is very costly. Some of the types of gearboxes are planetary gearboxes and the parallel shaft gears. High speed shaft. The speed and torque produced from the gearbox are transmitted for driving the generator with high speed shaft. This is present on the generator side of the turbine. Brake. This part is meant to stop the running of wind turbines during extreme weather condition. There are various types of brakes like mechanical brake, for examples are disc brake, clutch brakes. Aerodynamic brake, examples are tick brake and the spoilers. Another component is the generator. The conversion of rotational energy to electrical energy is carried out by the generator. In general, the wind-driven electric generator produces 50 cycle AC electricity. And the types of generators are synchronous and asynchronous. Electrically excited and permanent magnet are synchronous generators, while squirrel cage induction generators and slip ring are the asynchronous generators. Controller. The grid quality electric current is controlled by the controller of the turbine system. The controller starts up the machine at cut-in wind speed, that is generally 3 meter per second, and shuts off the machine at cut-out wind speed, generally 25 meter per second, as per the design requirement. So, they controls it. The controller measures and controls parameters like voltage, current, frequency, temperature inside the nozzle, wind direction, wind speed, the direction of yawing, shaft speed, overheating of the generator, hydraulic pressure level, correct valve function, vibration level, twisting of the power cable, emergency brake circuit, overheating of small electric motors for the yawing, hydraulic pumps, brake caliper and adjustment. Sometimes anemometer is also a part of this system, and it is an instrument that measures wind speed. It gives the input to the controller for power regulation and braking beyond the cutout and survival wind speed. Generally, anemometer is fixed on top of wind turbine. Pitch. The electricity production is controlled by pitch under different wind velocity. Blades are turned or pitched out of the wind to control the rotor speed and keep the rotor from turning in winds that are too high or too low to produce electricity. Tower, it is an important component. This helps to use the wind energy at sufficient heights above the ground. It helps to absorb and securely discharge static and dynamic stress exerted on the rotor, the powertrain and the nacelle into the ground. The major types of towers used in wind turbine are lattice tower, tubular tower, guide tower and hybrid tower. You can see the characteristics of different towers in this table. The tubular steel tower is having more area of contact and more loading with even load distribution, while the lattice tower has less area of contact and loading, but its load distribution is uneven. In guide tower, the area of contact and loading is less and the load distribution is also even. And the hybrid tower is a combination of tubular and lattice. The tubular towers are more popular among modern turbines because of their lower airflow interference and downstream turbulence creation apart from its more aesthetic acceptability. The tubular steel tower is costly, and the transportation and fabrication of lattice tower, the three-leg tower and guide tower are easy. Guide wire tower is suitable for the small wind turbines. Generally, the tower height is 1 to 1.5 times the rotor diameter and is normally about 20 meters. The optimum is considered as 30 meter height. The site characteristics have a great influence on the tower selection. Tower stiffness is an important factor in wind turbine system because of possibility of coupled vibration between rotor and tower. The tower shadow is the wake created by the airflow around a tower. There is an effect of tower shadow on turbine dynamics, power fluctuations and noise generation, especially on the downwind wind turbines. Foundation. The foundation type has been chosen based on the soil condition and water table location present at the plant site of a wind turbine. Onshore foundation types includes the slab foundation. It is preferred when the topsoil is strong. Pile foundation. It is preferred when the topsoil is of softer quality. Offshore foundation types are monopile, gravity base or tripod. Wind vane is an instrument which is used to measure the wind direction. It provides information to the controller for orienting the turbine properly, that is yawing with respect to the wind direction. Yaw drive. The function of this is to keep the turbine aligned to the wind. It turns the nacelle with rotor as per the wind direction using a rotary actuator engaging on a gear ring beneath the nacelle. Two types of yaw drive systems are active or free yaw systems. Active yaw drive mechanism is with yaw motors and is controlled by automatic yaw control system with its wind direction sensor mounted on nacelle in position when it is not in yawing. It's used commonly with upwind wind turbines. Free yaw systems can self-align with the wind and it is commonly used on the downwind wind turbine systems. And it is powered by the yaw motor. Let's see the classification of wind turbines. There are different types of wind turbine technologies. First, classification is based on the axis rotation. It is classified as horizontal and vertical. And based on number of blades, based on the numbers, we can classify that turbines into single blade, double blade, three-bladed and multi-bladed. Based on location, it is classified as onshore and offshore. Based on the power control, the turbines are classified as stall, variable pitch, controllable, aerodynamic. based on structure or yaw control or the yaw direction. It's based on the surface or yaw control or yaw direction. It is classified as driven yaw, free yaw or fixed yaw. Based on rotor position, it is classified as upwind and downwind. On transmission, it's divided as with gear and without gear turbines. Based on type of the hub, it's divided as rigid, teetered, hinged blade and gimbaled. Based on generator speed, it has constant and variable turbines. Now let's see the wind turbines based on the axis rotation. The common classification, this is the common classification. It is based on the axis type, and there are two types: horizontal axis wind turbine, which is known as HAVT, and vertical axis wind turbine, which is known as VAVT. Horizontal axis wind turbine, which is abbreviated as HAWT. Vertical axis wind turbine is abbreviated as VAWT. So the horizontal axis wind turbine, this is the most common type of wind turbine, and the axis of rotation of this wind turbine is parallel to the ground. In this wind turbine, the axis of blade rotation is also parallel to the wind flow. Commonly found horizontal axis windmills are aero turbine mill with 35% efficiency and farm mills with 15% efficiency. And the main components of HAWT are rotor with blades for the conversion of wind energy to rotational energy, and it costs around 20% of the wind turbine cost. The generator component consists of electrical generator, control systems and the gearbox. It converts low speed rotational energy to high speed rotational energy, which is needed for the electricity generation. It contributes to 34% of wind turbine cost. And the structural support, it includes the tower and yaw mechanism, which cost around 15% of the turbine cost. This is the pictorial representation of the main components of horizontal axis wind turbine system. The HAWT, the horizontal axis wind turbines, are classified based on the rotor orientation into upwind of the tower or downwind of the tower. Hub design, it is classified into rigid and teetering, rotor control, pitch and stall based on number of blades as 2 and 3 blades and multiple blades also. Based on how they are aligned with the wind, it's free and active yaw. Coming to the advantage and disadvantage of this horizontal axis wind turbine. This horizontal axis wind turbine is more stable due to position of blades of the horizontal axis wind turbine to the side of the turbine center of gravity. Efficiency is more because of maximizing the collection of wind energy by turbine by adjusting the angle of the attack. During storm, rotor blades are able to pitch and reduce this damage. Accessibility to strong wind is also possible in this turbine. It is suitable for areas with wind shear and placement on uneven land or in offshore locations. But it has disadvantages like facing difficulty in operating near the ground, difficulty in transporting heavy and tall towers and long blades, requires a special installation procedure, and it creates navigation problem at offshore sites. Vertical axis wind turbine. This axis is perpendicular to the ground. The vertical axis wind turbine do not take advantage of higher wind speeds at higher elevation above the ground. So, it is less common. The best vertical axis designs are Darius wind turbine, which has curved blades and efficiency of 35%. Giromil wind turbine, which has straight blades and efficiency of 35%. And another one is the Savonius wind turbine, which uses scoops to catch the wind, and the efficiency is around 30%. The advantages of vertical axis wind turbine are no need of wind turbine to orient with respect to wind direction. It has lighter weight. It is easy to maintain because the shaft is vertical. The transmission and generator can be mounted at ground level, and cost is less. But the vertical axis wind turbine is not as efficient at collecting energy from the wind in comparison to horizontal axis wind turbine. The wind energy conversion depends on optimum tower height, control systems and number of blades and the blade shape. The design of wind turbine, it is based on the number of blades, rotor orientation, blade material, construction method, hub design, power control, rotor speed, orientation of the turbine, type of generator, gearbox or direct drive generator. The different parameters like solidity, blade tip ratio, rotational speed are also important in designing a wind turbine. Solidity is the ratio projected area of blade to the swept area. You can see the solidity by this example. A windmill has a rotor of 6 meter with 30 blades. Each blade has a width of 0.39. What is the solidity? It is equal to 30 into 0.39 by pi into 6 square 100. The blade tip speed is the another parameter. It is calculated from the rotational speed of the turbine and the length of the blades used in the turbine. Blade tip speed is equal to rotational speed in RPM multiplied by pi into diameter divided by 60. The tip speed ratio is very important factor in the different formulas of the blade design, and it is equal to this tip speed ratio. Lambda is equal to tip speed of the blade divided by wind speed. For a particular wind speed, there exists an optimum turbine tip speed for producing maximum output. The slow running multi-bladed wind turbine rotors operate with tip speed ratios in the range 1 to 4 and fast runners use 5 to 7 as tip speed ratios. So, it is important to match the rotation of the wind turbine to the corresponding wind speed. Estimate the tip speed ratio if the rotational speed of the turbine is 20 rpm and diameter of 6 meter and wind speed of 4 meter per second. So, blade tip speed is equal to rotational speed into pi into d by 60. So, you will get 6.28 meter per second. Tip speed ratio, the tip speed of the blade we have already calculated, divide it by wind speed which is given 4. So, we will get around 1.6 is the tip speed ratio. Now, how the generator capacity, rotational speed, wind speed and swept rotor area of the turbine are related. We need two formulas to explain this. One is power equal to 0.6 into Cp, it is the power coefficient, multiplied by N which is the efficiency of the driven machinery, multiplied by A which is the swept rotor area, and V cube, that is the velocity of the wind. And another equation or formula which we need is for the rotational speed in RPM, which is equal to V into, that is the velocity, into tip speed ratio into 60 divided by 6.28 into R. R is the radius of the rotor. So, this concept normally works without transmission. But if a transmission with efficiency is there, so the efficiency is not 100%, so we should multiply with a factor of 0.95. So, then the N, the efficiency of driven machinery will be N is equal to 0.95 multiplied by 0.7. Now, how to find out the blade chord? Blade chord is equal to 5.6 into R squared by I into Ci into R into TSR squared. That is 5.6 into radius of the radius at tip divided by I, that is the number of blades, multiplied by lift coefficient multiplied by the radius at point of computation, and it is multiplied to the tip speed ratio, square of the tip speed ratio. So, calculate the rotational speed and power output of the turbine having a tip speed ratio of 7, rotor efficiency of 0.4, generator efficiency of 0.7, swept rotor area of 2.11 meter square and radius of rotor of 0.82 meter. So, for this just apply the equations. For the rotational speed, that is velocity multiplied by tip speed ratio into 60 divided by 6.28 into radius at tip. Then we will get rotational speed as 701 rpm. And the power output, apply this formula of 0.6 into the power coefficient multiplied by N multiplied by A, that is area, multiplied by cube of the velocity. We will get 226 watt. This is the figure which shows the wind turbine design and the power output progression over the years. You can see the designs, the development of the design and the efficiency of the designs has increased. The variable wind speed fluctuate the output voltage and power. It leads to flicker effects, voltage asymmetry. This affects the power quality of the network or the grid system. Fixed speed turbines produce a power pulsation emanating from the wind shear over height. So variable wind speed turbines are helpful as they are able to absorb short-term power fluctuations by using immediate storage of energy on the rotating drive tray. The process of controlling the velocity of the wind turbine is known as pitching, and the speed of the wind turbine can be controlled by changing the orientation of wind turbine, pitch of the blades, and this helps to modify the aerodynamics, and hence the efficiency of the wind turbine can also be improved. So to conclude, we have seen in this module various components of wind energy conversion system like aero turbine, gearing, coupling, controller and the electric generator. We have seen the components of wind turbine in detail, and these are grouped into rotor with hub and blades, transmission and control, and the supporting structures. We have seen the classification of wind turbines based on different factors and mainly based on the axis of rotation into two groups, horizontal axis wind turbines and vertical axis wind turbines. In horizontal axis wind turbine, it is parallel to the ground, while the turbine in the vertical axis wind turbine works perpendicular to the ground. And we have seen the advantages and disadvantages of both these turbines, and the commonly used one is horizontal axis wind turbines, and some of the vertical axis wind turbines are Darius, Savonius, Guromil, etc. We have seen that horizontal axis wind turbines are more efficient, while the vertical axis wind turbines does not need any control system for the orientation, so that it can be used for wind from any side. We have seen how to design the wind turbines, what are the components to be taken care while designing the wind turbine in an area, and also the parameters which are to be considered like solidity, tip speed ratio, rotational speed, etc. also we have seen. Thank you.